Have you ever wondered why your grandma's cookies taste so good? One day you just simply ask her, "Grandma, why are your chocolate chip cookies so good?" And she responds with a very long story how a recipe was passed along. And she followed the same exact ingredients in the recipe. So she had the exact amount of eggs, the exact amount of flour, the exact amount of chocolate. But the only thing that she really had to change was how long she had to bake the cookies for. She realized that sometimes baking the cookies for 20 minutes isn't the best idea, so they'd come out as burnt. And then after some time, after a whole bunch of trials, she realized that, okay, after baking the cookies for 12 minutes, that was the perfect number. And exactly, that's pretty much how hyperparameters work, tweaking these numbers so that you get the best value. And in this case, it was the amount of time that she took to bake the cookies, which was 12 minutes. And at the end of the day, scientists aren't perfect and they do trial and error runs, and that's exactly what hyperparameters are similar to.
So I want you to imagine that you want to play guitar for your friends and you just sort of pull the guitar out of the closet. It's completely out of tune, you start playing, it sounds terrible. So you decide, all right, I've got to tune it. But you don't have a tuner, so you just kind of start randomly twisting the pegs. Maybe you get the A right, but all the rest of them are out. You play a chord, it sounds terrible again. The more, you're gonna have to do this over and over. You're gonna have to keep kind of making random choices until the guitar overall sounds like something you could actually, play a song on. Whether you play guitar or you don't play guitar, it really doesn't matter. If the instrument's completely out of tune, it's gonna sound bad, no matter if you're, Jimi Hendrix or some kid who's just the Guitar Center for the first time. The crazy thing is that there's something in machine learning that's very similar to this, and it's called hyperparameters. Machine learning is a science, but even in a science, there's some guesswork, and this is one of those areas. In a model, there are both parameters and there's hyperparameters. Parameters are things that you understand, that you can describe, that might be the mass of something, et cetera, et cetera. They're measurements, they mean something. Hyperparameters are more like just kind of arbitrary numbers, they're just figures. And when machine learning scientists are trying to make a model work, they just sort of insert random numbers into their models, much like you would do if you're just twisting pegs on a guitar. The weird thing is that there's thousands of these, hundreds, thousands, God knows how many. And eventually you can get to a kind of more optimal mixture of those figures. But along the way, what you're doing is you're kind of like crossing things off a gigantic list of potential hyperparameters. And there's sort of, much like a guitar, there's an art to this, and it takes time. And it is a little counterintuitive that something that is a science involves this much guesswork. But it's one of the kind of, in my mind, really interesting and kind of exciting things about machine learning.
You know how scientists build model for everything? You can think about a model as an equation that has a set of independent variables mapping to a target. These equations have a set of parameters that would influence the prediction of the model. Tuning these parameters is essential for you to better fit the real-world data. These parameters could be tangible in most cases. If I were to give you an example of a tangible parameter, think about a model that predicts the spread of an infectious disease. The tangible parameter in this case would be the average number of people an infected person could infect. Unfortunately, not all of the parameters in the building of a model is tangible. In some cases, you would have one non-tangible parameter that would influence the prediction of a model. If you have one non-tangible parameter, chances are that you have more than one influencing the prediction or training of the model. If I were to give you an example of a non-tangible parameter, think about the combinations to open up a lock. The brute force way of finding the right combinations to open up a lock would be to try different combinations until you arrive at the right combination that opens up the lock. Of course, you could be like smarter about it by listening to the click until you arrive at the right combination that opens up the lock. In this case, you'd be faster at arriving at the result, but you would have like no reasoning, or you can't explain why those sort of like the combination that you tried worked. Unfortunately, this is the case when like deep learning engineers build models that help predict a specific task. They have these like set of like hyperparameters that they try or brute force until they arrive at the right combination that helps predict the model better.
If you've taken a machine learning class while pursuing your degree, you might have heard of something called hyperparameters. These are basically parameters or settings on a machine learning model. The thing is that finding the right hyperparameters for a machine learning model is a really important task, because it's the difference between your model performing really poorly versus it performing really well on the test set. For example, with bad parameters, you can get low accuracy, like 0% or 5% accuracy. With good parameters, you can get 90% accuracy or better. But this is just an example. So an active area of research is looking into better ways to solve for hyperparameter search and finding the right hyperparameters for your model so it performs the best as best as it can. What's the basic, one of the basic approaches to solving for hyperparameters is something called grid search. Grid search is a brute force approach in which you manually go through every single one of the set of hyperparameters in the search space. This is sort of a dumb approach because this would be really expensive to do and computationally very significant. And as a result, doing this in the real world is not really feasible. So what's a smarter way of approaching something like this? Well, one way that is really effective, that has shown promise, that people use in both academia and industry, is something called Bayesian optimization. Bayesian optimization is fundamentally based in something called Bayes' theorem, which is a method for calculating a conditional probability. What Bayes' theorem or Bayesian optimization tries to do is it tries to estimate the objective function of a machine learning problem. So typically a machine learning problem is going to be defined by something called an objective function. It's a formal definition of the problem space. The thing is that many machine learning problems, objective functions, cannot be solved analytically, or the solution is not going to be resulted in a linear time. And so this means that computing the objective function solution is either intractable or way too computationally expensive. So an approach here is instead of calculating it directly, we can sort of get a general idea of where to go by using Bayesian optimization and Bayes' theorem, so that as it's going through the hyperparameter search space, you're guiding it towards the right direction incrementally. Essentially, this is how Bayesian optimization is a significant improvement over something like grid search, and this is why it's so frequently used in industry.
Will we ever truly understand those pesky hyperparameters? Of course, I'm not talking about the mathematical meaning. We all know what a number of epochs, a number of layers, or a batch size stand for. I'm talking about understanding the reason why a specific value would turn out to be optimal for a specific hyperparameter. And even those of us who are extremely good at hyperparameter tuning a model might still not claim that they truly understand them just because they understand some of the heuristics. So I was trained originally as a particle physicist, and I've spent years trying to make a contribution to what scientists call the standard model of particle physics. That's basically one big equation trying to explain the behavior of every single particle in the universe. In other terms, it's just one gigantic equation trying to summarize the entire universe. Pretty ambitious, right? And so at first, I thought that my job as a particle physicist was to try to build models to measure as many of those parameters as possible. But then eventually I found out that a lot of scientists were actually just using arbitrary values that just made the model look right and closer to reality. For example, You might not know that, but even the gravitational constant is something that no scientist truly knows why it has this specific value. And so later on, sometimes some scientists would discover a new way to actually measure those arbitrary parameters. And sometimes they would find out that some of those constants were actually not a constant at all, and they had to be replaced by an entire new mathematical formula, because we had made some progress in theoretical physics, and it was clear that it was not a constant at all. So sometimes I wonder if the exact same thing isn't happening with deep learning. In fact, did you ever wonder if the fact that we still don't know how to explain those hyperparameters was actually nothing else than a sign that we still haven't done enough modeling? Well, only time will tell.